Yeah, so good afternoon, students. We were learning moving of a charged particle in a magnetic field, movement or motion of a charged particle in a magnetic field. And I think I was able to tell you that if there is a velocity component, perpendicular to the magnetic field, the particle moves in a circle. It moves in a circle. Next, I think I was also able to tell you that if there is a component perpendicular and parallel to the B, then it moves in a helical path. So I explained to you that the radius is because of the perpendicular components. Then the pitch of the helix depends on the parallel component. So last class we had just discussed this, and I had explained to you about a cyclotron, and then we had discussed about what is a cyclotron and how a cyclotron works. I think I had just completed that. What we will do now is we will just move on from there. Yeah, upcoming test portion is the entire current electricity. Next week is full current electricity. I was surprised today. Today one parent calls me up and he asked me, is there any test for the 12th student? And I was surprised when the parent said that their child is not aware that there is any test. Okay, so I think each one of us here should take up the responsibility when it is being announced so many times during the class and later, unless while we are doing the class you guys are on some other site, I don't know. Okay, so yeah, so last class I completed cyclotron, and we'll just move ahead from there. So the next thing that we have to learn, we have almost finished learning about the movement of a charged particle in a magnetic field. There are just few small things which I want to complete, and then we can move on. So suppose there is a magnetic field. Suppose there is a magnetic field, let's say in this direction, and if there is a charged particle which is going like this. Now the charged particle, if I stretch my right hand, and then if it's a positively charged particle, it will have an upward force. That upward force is equal to Q into V cross B. Yeah, Q into V cross B. If there's an electric field in this direction, it has experiences an electric force Q into E. So now Q into V cross B is equal to Q into E. So the Q's will get cancelled. So I'll get V is equal to E by B. That means if the charged particle has a velocity which is equal to E by B, the net force of the charged particle is 0 and the particle moves in a straight line. The net velocity on the charged particle, the net force on the charged particle is 0 and the charged particle moves in a straight line. Now if V is less than this velocity, then the electric field will be more, and then it goes in this direction. If V is greater than this, then this will become more and it will go this way. So if I have a system of particles each at different velocities, and I want to pick up those particles which have a specific velocity, all that I have to do is I have to push it through a region which has this kind of an electric field and a magnetic field. Okay, so In this case, velocity is a particular velocity goes without any deflection. Higher velocity or lower velocity gets deflected. Thus, this selects particles. This selects particles having a specific amount of energy, and such a device is what is referred to as a velocity selector. Yeah, such a device is what is referred to as a velocity selector. A velocity selector selects particles of a specific velocity which will pass through without getting deviated. The ones which have a greater or a lesser velocity will either move up or will move down. Yeah, so if you are able to understand this, please make notes and then we will move on. So this is a velocity selector. Velocity selector selects those particles which have a particular velocity. Greater than that or less than that will move in opposite directions. Okay, so once you understand this, then we will move on. The last class somebody was asking me how will you select particles. You just push them into a magnetic field. Once you push them into a magnetic field, depending on the Q by M ratio, they will all be moving with different time periods. So based on that, you will be able to select particles. QVB is equal to MV square by R. Cancel these two. So you will get R is equal to MV by BQ. Then the time period is equal to 2 pi R by velocity. So that will become 2 pi mv by v into bq. Cancel these two. So that is equal to 2 pi m by bq. So this 2 pi m by bq is the frequency, is the time period. So you see that the time period depends only upon m by q ratio. M by Q ratio means it means each particle, each type of charged particle will have a specific M by Q ratio. The time period is also going to determine the frequency with which you are going to oscillate the, you're going to change the electric field. Okay, so only those particles which correspond to that particular M by Q ratio will get accelerated. The others won't get accelerated. Okay, so cyclotron will help you separate charged particles. It helps you accelerate particles, and then it helps you get high energy particles. As far as electrons are concerned, the mass of an electron is equal to m0 divided by root over of 1 minus v square by c square. So as v becomes large, that root over of 1 minus v square by c square becomes small, and the m becomes large. When m becomes very large, the cyclotron, you can't, the frequency of the cyclotron keeps varying, and once the frequency of the cyclotron keeps varying, you will find it very difficult to operate or make it work. So that is why very small particles like electrons are not, a cyclotron is not suitable for accelerating electrons because of the low mass. See, this is a region where you have a electric field in this direction. So if you have a charged particle going like this, a positive charge particle, it experiences a force in this direction. So that force is equal to Q into E. Okay. Now in the same region, you have a magnetic field which is into. So if you have a magnetic field which is into, now for this velocity, if you do Q into V cross B, the force will come in the upward direction. So QVB will be in the upward direction. So on the charged particle, there are two forces, QVB and Q into E. Now if these two are equal to each other, Q gets cancelled. So V becomes E by B. So for a particular velocity or for a particular E by B ratio, now if the velocity is equal to E by B, then the particle will move in a straight line. Why will it move in a straight line? Because upward force is equal to downward force. Because upward force is equal to downward force. On the other hand, if electric field is more, or if velocity is more, then this magnetic force will be greater. So if magnetic force is greater, then the particle will go this way. If velocity is less, then the electric force will become greater. So the particle will move in this direction. So those particles which have a greater velocity or a lesser velocity get deflected, and only those which have a specific velocity pass through. So that is why this is called a velocity selector. So it will select and give you particles of a given velocity. Okay. Yeah, so this is a velocity selector. I don't know, I hope you guys are able to listen to me today. There is no question, there is nothing. Okay, so let me finish off my other works, and then again slowly we will move on. Now, so suppose there are a few other small questions which I want to answer. See, suppose a particle, this is on this side there is a magnetic field B, on this side there is no B. So here if it was moving in a straight line, it will continue to move in a straight line. The moment it enters here, there will be, the moment it enters, there will be a force in this direction, positive charge. So it will go like this and then it will emerge out. Okay. So what happens in the magnetic field is no work is done. No work is done. So there is no change in velocity, no change in speed, I'll say, because we are talking about the magnitude. But there is a force acting, and what does the force do? The force makes sure that there is a direction change. There is a direction change. And please note that the particle entered perpendicular to the magnetic field and will also leave perpendicular to the magnetic field. The particle entered perpendicular to the B and left perpendicular to the B. Okay. Now, the question that I want to ask is, what if it goes at an angle? Okay, suppose it goes at an angle 30 degrees. So what? Yeah, the magnetic field is still perpendicular this way. But now what will happen is the center of the circle will be somewhere here. So the particle will continue to go this way and it will leave somewhere wherever it leaves, even there, the particle will go perpendicular to it. Now, the angle at which it entered the magnetic field will be same as the angle at which it will leave the magnetic field. Please understand that this is 90 degrees and this is also going to be 90 degrees. Okay, so if there is a particle, if there is a limited magnetic field, and if a particle is entering that magnetic field, the angle at which it enters the magnetic field will be equal to the angle at which it will leave the magnetic field. Okay, so this will enable you to, this understanding will enable you to work out a few questions which may appear. There was a question in a JEE advanced paper before like this, so this is how you could have worked it out. Well, commercial application, when you have a cyclotron, you would want particles which have specific energy. So how do you know the cyclotron, they have a specific energy? So you pass the particles through a velocity selector. So once it passes through a velocity selector, then you know where it will go. Not just this, your television, the earlier days, picture tubes used to be working on this concept. There used to be a varying electric field and magnetic field, which are coming from the EM wave of the signal. So based on the magnitude of the electricity part or the magnetic field part of the wave, the particle would go and hit different points on the screen. So when it hits different points on the screen, those particular areas get brightened up. So the first cathode ray tubes were based on this concept. So the first generation picture tubes, the cathode ray tubes, which were used to watch movies, are based on, which was used for a television, is based on this. Earlier days, the televisions used to have a picture tube. So the picture tube is based upon the same concept. There is a mutually perpendicular electric and magnetic field. Depending on the signal that we get, there will be electrons which would be pushed to a differential levels, and accordingly they will hit different points on the screen. Okay, now this is the fifth slide. I'll explain this again. See, there is a magnetic field only in this portion. On this side, there is a magnetic field. On the other side, there is no magnetic field. So if on this side there is a magnetic field, then suppose a charged particle is entering the magnetic field this way. So if a charged particle is entering the magnetic field this way, then this is the perpendicular component. The center is here. So the charged particle tends to move like this. The charged particle will tend to move like this, and at some point it will move out of the magnetic field. Now wherever it moves out of the magnetic field, even at that point, this will be perpendicular. Yeah, so this is a perpendicular. So the moment this is a perpendicular, we can now try to find out what the angle is. What I can explain to you is this, is that, so the magnitude of the velocity here and the magnitude of the velocity here is the same. So the particle moves tangentially out. Now, yeah, so I just have to think a little and then work a little. That's it. If you just think a little, it will come out. So this is a parallel line. So yeah, this is also parallel line. So this angle is theta, this is theta, this is 90 minus theta, this is 90 minus theta, this is 90 minus theta. Okay, so if this is 90 minus theta, this is 90 minus theta. So this angle here is 90 minus theta. So now, yeah, that's the angle. That's the angle that we're talking of. So this whole thing is 90 degrees. So this angle is theta. So yeah, so now the geometries are all clear. Okay, so that is what I was referring to. So yeah. If you're not able to find out the exact velocities, don't we violate uncertainty principles? Don't worry, physics is not so simple. Physics is not so simple. There are many, many more questions. That is why we are still working. Otherwise, mankind would have known everything. If everything was as easy as I was telling it, then we have already known everything and now we can move on. There's nothing more to learn. No, this is just practical theory. When you go to practicals and when you work with it, there are 1001 more problems you will face. Uncertainty principle is another problem which we will have to learn how to solve it. We don't want to care about that right now, but those of you who want to go out and then do more work, definitely you will see that this is not all. This is just a small portion, and all these cannot be achieved without very careful calculation and without the use of advanced computers. So yeah, so that is why you still don't have many cyclotrons in India. In US, institute like Berkeley has a few of them. In California itself, there will be at least 5-6 cyclotrons. Now, in whole of Chennai, I doubt if there is a cyclotron. Maybe there is one. Maybe we have one. Definitely, we have one in Mumbai. I doubt if there is one. There is one in IISc in Bangalore. You have one. Other than a few handful of cyclotrons, I don't think we have many cyclotrons. And cyclotron is like something that was there in every US university 30-40 years back, right? So yeah. So we are talking about a lot of difference. Okay, so if you understand these, we're doing good. Focus on basic understanding. Beyond this, there are lots of issues which you all will have to solve. Yeah, so if you are able to find out the exact velocity, so Sundaram, I hope you got my answer. Yeah, CRT monitors are all based on this. Okay, so yeah, good. So if you all understood this, then my job is a little better. And then let me go back. So now I told you that if there is a charged particle placed in a magnetic field, it experiences a force which is equal to Q into V cross B. Okay. Now I am saying that it is Q into V. V can be written as the dl by dt cross B. Yeah. Now suppose I take the Q inside and bring the if I take the Q inside, then what will I get? I will get Q by dt, or I just bring the dt outside. Dt is a scalar quantity, so I bring it outside. So I get Q by dt dl cross B. Now what is Q by dt? Q by dt is I. So we have I dl cross B. So what it means is that if you have a current carrying conductor, if we have a current carrying conductor, carrying in a magnetic field, in an external magnetic field, there is a force acting on it. Because current is nothing but moving charge. So if current is moving charge, then the charge is having some velocity. So based on that, I can say it is equal to this much, right? So this is the force acting on a current carrying conductor placed in a magnetic field. So if you take a current carrying conductor, place it in a magnetic field, this is the force. Suppose I take a conductor of length L and this is the magnetic force and it carries the current in this direction. Then according to the right hand rule, if you stretch your right hand with the fingers pointing in the direction of current, curl the fingers down towards the magnetic field, the thumb points in this direction. So there is a force acting in this direction. And what is the force equal to? I B L. So this is the force acting on the conductor. Do you understand this? So we started with moving charges and slowly now moving charge is nothing but a current. So there is actually a force even acting on a conductor, and that force is equal to B into I into L if it is perpendicular to it. But here of course that helical motion and all those things will not be possible. We can only talk about the perpendicular force which is acting on the coil. Yeah. So is this understood? Yeah, are we able to understand that if there is a current carrying conductor placed in an external magnetic field and there is a current through it, it experiences a force, and that force is equal to B into I into L. B for magnetic field, I for current, L for the length of the conductor. Okay, so if this is understood, then slowly I will move ahead. Suppose there is a magnetic field like this, and you have a conductor like this. This is having a length L, so it will have a force, and that force is equal to B into I into L. That force will be in this direction if the current is in this direction. Okay, so current is the assumed movement of positive charge. So positive charge is going like this. So the force is equal to B into I into L. Okay, so if this is understood, then I will move ahead. Yes, I don't know, all of you, where are you all? You're there? Okay, so good. So if it is understood, then quickly I'll move to slightly more complicated things. Suppose the magnetic field is in this direction. Suppose there's a wire which goes like this and which moves like this. It goes this way, it goes this way, it goes this way. Then, and there's a magnetic field B in this direction. So now what is the force? Current is I. What is the force acting on it? So now we can find out the force acting on it. To explain to you what is the force acting on it, here the current carrying element, the dl, is like this. So I can say that dl consists of two parts. There is a dx part and then there is a dy part. So there's a dx, there's a dy, there's a dx, there's a dy. So there's a dx dy, so there's a dx dy. Okay, so there's a dx dy, dx dy. So I can put all the dx's together, so I get it here. Then I put all the dy's together, I get it here. Then I bring all the dy's here. Then again I put all the dx's together. So this bent wire is equal to a current going this way, this way, this way, and this way. Because the current here is 0, there is no force in that direction, and this length is equal to r, this length is equal to r. So I can say, suppose this one was L1, L2, so it will become L1 plus L2 plus 2r, then Bi. So this is going to be the force acting on the wire. A force acting on the wire with a current in this direction is in this side. If the wire was going this way, the force would have been on this side. Okay, so along the x-axis, if the current goes, the force is along the y-axis. Along the y-axis, if the current goes, the force is along the z-axis. So now I am saying here, when you travel from here to here, you are going some distance. When you're going from here to here, you're coming back that distance. So the net force on that along the y-axis will be 0, and there is a force only along the assuming that the wire is only of radius of length 2r along the x-axis. So the net force is given by this. This is a question which has come quite a few times in your entrance exams. You will not get such questions in your NCERT syllabus. In NCERT, we do not have bent wires. Okay, we have only wires, straight wires. Yeah, so this is required only for entrance exam. If you understand what I taught here, this is all that is there in the syllabus. Okay, my approach has been that if there is a DL, that DL will have a dx and dy. So I am putting all the dx's together. Similarly, I am putting all the dy's together, all the dy's together, all the dx's together. So here there is a current going this way and there is a current coming back. So this is 0. So it is equal to a current which is there between the two straight points. So whether I have a straight wire or a bent wire, the force on the wire is going to be the same in this direction, B I to R. Okay, I'm assuming there are no side lengths. Okay, so yeah. So here it is, here it is. So please make some notes and then we will move on. This is the force acting on a current carrying conductor placed in an external magnetic field. So when you put a conductor in an external magnetic field, it has some force. So we are talking about that force. Yeah. Yes. So I hope some understanding is there. This is the one. Then the next slide was this one. Okay. So if you have a wire which goes from here and suppose it goes here so much, and then again it continues like this, 3/4 of a circle, then you go up to the center, go up, again come down, again go this way, again go this way, again go this way. So here there is no force, here there is no force for a current going this way. So this is equal to a current this way. So suppose this is L1, this is R, suppose this is L2, this is R. So the current goes this way and comes this way. So because of this, it is B I L1 plus R. The force is in the y direction. Then again on this, it will become plus B I L2 plus R. The force is in this direction. So I'll say I cap. So this is the net force acting on this wire. This is the net force acting on this wire, which means that if there is a full circle, the net force acting is 0. This question has come in the NEET exam. This question will come in the NCERT board exam, because we will be seeing that on a closed loop, the net force is equal to 0. On a closed loop, the net force is equal to 0. Yeah. I don't know, Levin, what you're trying to say, but I am trying to say is this, that the force acts, magnetic field, we have taken always in this direction so that we understand it better. So the magnetic field is like that. If you do the right hand rule, stretch your right hand in the direction of current, curl your fingers towards the thumb points in the direction of force. So thumb points in this direction. In this case, the thumb points in this direction. So for the X wire, the force is along the y direction. For the y wire, the force is along the x direction. So this is equal to the net force which is acting on the on this particular wire. Yeah, okay, okay. Okay, so force acting on a closed loop is 0, right? So if you all are understanding this, then I'm good to go. So now just suppose there is a wire like this, and it's inclined up to a particular angle such that this angle here is known to us. If this angle here is known to us, then this is equivalent to a wire which goes up to that particular point. So I'll put it in red. So it goes up to the particular point, and from there it comes this way. So this is r, this is r cos theta, this is r sin theta. So I mean, ignore this if you want to. So it is b I r plus r cos theta. So the force, the current going this way, the force is along the j cap. Then again, the current is going to for this, the current will be like you are going all the way up, and then you have come down up to this particular point. So the current is in the upward direction. So upward means force is along the minus. So b I r sin theta I cap. So this is the net force acting on this wire, which is up to some angle theta. So this is equal to a current going this way, and then a current reached up to that particular point. So they can give you bent at 180 degrees, bent at right angle. So if there's a wire which is going from here and then it goes like this, now what is going to be the force? This is equal to up to here and then up to here. So it will become r b I r j cap minus r I cap. That is the net force. Yeah, so whatever be the geometry, as long as it is part of a circle, you will be able to answer the question. Yes, okay. Okay, so if you understand the question, then the important question that we're going to ask is what happens if there is a loop? So what happens if there is a loop? And then we answer that question and move to the next big concept. Now, suppose I have a loop of this kind, a rectangular loop of this kind. Yeah, suppose there is a magnetic field here in this of this kind. Suppose there is a current going this way, current going this way, current going this way, and this way. So if there is a current this way, so on this particular part, I will see that there is going to be, if I apply my right hand rule, please work with your notebooks, please don't assume. Stretch your right hand in the direction of the current, curl your fingers towards P. So the thumb will point in this direction. In this case, the thumb will point in this direction. In this case, the thumb will point in this direction. In this case, the thumb will point in this direction. So the net force is equal to 0. Yeah, the net force is equal to 0. But the moment this loop is inclined at a small angle, there will be a torque acting on it. So this is the next thing that mankind discovered, that the moment you pass current through this particular wire, that wire will start rotating. And from there, mankind could discover motors, and this led to the next big round as far as the big change, as far as the industrial revolution is concerned. So this is what made the late 1800s, I mean after 1850, all the way up to 1900, not just 1900, 1920, 1930. The first part of the industrial revolution, that is from 1700 to 1750, 1780, 17, all the way up to let's say 1800, was led by steam. Steam power ruled the world. And now the electric motor started taking over. So steam was going down and the electric motor started coming up. Okay, so if this is understood, then this is understood, then we will discuss more about this. Electric motors, DC motor, AC motors are not there in your syllabus, but there is another device which is there in your syllabus which will help us understand this as well. Is the last question required for both? Nowadays we have moved out of nuclear. Nowadays we have moved out of nuclear. It is solar power. Is the last question required for boats? No. Bent wires are not there in your boats, but loops are there in your boats. This is there in boat. Very important question. This is not required. No bent wire. This is not required for boats. Only the straight wire is required. So these loops are required. So they'll ask you, I think last exam also there was a question, last this 2020, what is the force acting on it and what is the torque acting on it. So we will work it out. Okay, so to work that out, let us assume there is a magnetic field in this direction. Okay, now let the magnetic field be equal to B. So here is the loop of wire which is placed in the magnetic field. Now suppose you pass a current through it. Suppose you pass a current through it. Now if you pass a current through it, what is going to happen is, let me look at this particular wire. Stretch your right hand in the direction of the magnetic, in the direction of current, then curl your fingers towards the magnetic field. Okay, curl your fingers towards the magnetic field. So if you curl your fingers towards the magnetic field, you will see that there is a force on this in the downward direction. Same way, you will see there is a force on this in the upward direction. The reason why I drew the magnetic field in the plane, only now you will appreciate the rotation part. So if you take this as the axis, now there is a force here, BIL. There is a force here, BIL. Now torque is equal to R cross F. So this R is going to be the width. So there are two forces, to 2 times width by 2 into F. F is what? Cross BIL. Okay, F is equal to BIL. Now I just bring the L to the other side, and then I will see that first this 2 gets cancelled. I'll bring the L to this side. L into omega is nothing but the area. So it becomes A cross B. So it becomes N for number of turns, I for the current, A cross B. This is the torque acting on this. Okay, torque acting on this is equal to NI A cross B. So that is equal to, I mean, the A cross B is not important. NIAB sine theta. NIAB sine theta. Where theta, what is theta? Theta is the angle between what? Angle between the width vector and the force vector, or you can say area and the magnetic field. That means if it is like this, if it is like this, if the wire is like this, still there will be, now the area vector is parallel to the magnetic field. So now the area is parallel to the magnetic field. So in this case, there is no force. So as it keeps rotating, as the value of theta changes, the force keeps changing. Now, so the torque keeps changing. So this is the torque acting on the wire. This is the rotatory effect. In effect, when you take a coil and pass a current through it, it starts rotating, but the torque is not a uniform torque. The torque depends upon the angle. As the coil changes its angle, the torque changes. That is why you need a kick to start it. Yeah. R is the distance of the force, point of application of the force from the axis of rotation. So if this full thing is W, this much is W by 2. So that is why it became W by 2. Okay. This is the magnetic field. Okay. Now, this is a rectangular loop present in that. It is carrying a current. Okay. Look at this loop. Stretch your right hand. When you stretch your right hand in the direction of current and curl your fingers towards B, the thumb points downwards. So this point is being pushed downwards. Okay. What is the force? B I L. It is being pushed downwards with the force B into I into L. If you look at this point is being pushed upwards with the force B into I into L. Okay. Now I am assuming that the axis of rotation is here. You take your notebook. On one end of the notebook is the upward force, on the other end of the notebook is a downward force. So how will it rotate? It will rotate. How will it move? It will rotate about its center. So it is rotating about its center. So this whole thing from here to here is the width. So here to here is the width by 2. Now the definition of torque is equal to R cross F. So torque is equal to R. What is R? Here there are two forces. So 2 into R is this distance. Radius is the distance from of the point of application of the force from the axis. So R cross F. So R is W by 2 cross F. F is BIL. Now, if there are n loops, I have just taken one loop, but suppose there are n loops in it, so it will become n times. Bring the L this side. If you bring the L this side, 2 gets cancelled. Length into width is nothing but this particular area. So it will become NIAB sine theta. So this is the torque acting on the loop. N for number of turns, I for the current, A for the area of the loop, B for the magnetic field, sine theta. Sine theta is the angle between the area vector and the magnetic field. Okay, so this is NIAB sine theta. Is the torque a constant? Obviously, no, it is not a constant, because as the torque keeps it keeps moving, there will be a differential torque. Specifically, suppose the magnetic field is like this, and if the orientation of the wire is perpendicular to it, now the area vector is in this direction. The force, the magnetic field is also in this direction. So now torque is least. Okay, torque is least. But because of inertia, it will keep moving. Once it starts moving means because of inertia, it will keep moving. That is why we need to kick. A DC motor has to be started. So even a generator, you will have to give it a pull. is your vehicles have to be started. If there is no starter, it was not going to start. The earlier generation had to be kicked. Bikes even today have to be kicked. So they all have DC motors and then they have to be kicked. Sometimes in your fans, when the fans become old, you got to move it. Once you start moving, then it picks up, it moves. But there is a starting problem. So starting problem happens when the orientation of the coil is such that the torque on that is 0. Now it doesn't move, but if you give it a slight push, then it will start moving. Yeah. Okay. So the moment there is a sine theta indicates that the force is not, the torque is not uniform. The torque is a varying torque. Okay. So fine. So based on this, you have an instrument called the galvanometer. So we will read a galvanometer. At max it is perpendicular. Yeah, at max it is perpendicular. At this it is perpendicular. Area vector is always perpendicular to the plane. So when the area is like this, the magnetic field, the area vector is upwards. Now if there is a field like this, it is perpendicular. So the torque is maximum. Okay, but in this position, the area vector is in this direction. If the area vector is in this direction, then the torque is minimum. So as the area vector changes, the torque changes. As the torque changes, so the rotation changes. Okay, so this is the way a DC motor works. AC motor also works in a similar way, just that there is something that you have to add to it to make it work for an AC. This is not there in our syllabus, so we don't have to work with it. We have a galvanometer in our syllabus. So in the next class, I'll explain to you the principle of working of a galvanometer. And once we do galvanometer, we are done with moving charges, and then we have to go to the next part. This chapter has 2 parts to it. The first part will be over. Then we'll be going and learning the second part of the same chapter. Okay, so I am done for the day. I have explained to you whatever I need to explain. Yeah, so there was a question in yesterday's exam where you had to work out 80 by 3. 80 by 3 is 26.67, which when rounded off will give you 26.7 and not 26.6. Okay, it will give 26.7. So there's an error. We'll have to sort it out. Yeah. Okay, so if you all want to see any specific slide, you may let me know. Okay, so slides from first. Here, slides from first slide. Second slide. Third slide. Fourth. Fifth. Sixth. Seven. Eight. Nine. 10. 11. 12. 13, 14, 15.
Hello,
Okay.
sir.
Yeah.
I just want to make an announcement. From tomorrow
Yeah,
onwards, we are
please.
using the new link. That's why.
Okay. Okay. Please tell them.
Yeah. The students, just listen from tomorrow onwards, as was told in the last week. Due to some security reasons, we are changing our links, ID and password. I have already shared the link. I hope everybody can see that. I will even share the ID and password also. Okay. I'll just share it in the chat. Already the link is shared. The ID I'm going to type. 867 2431. So no need of copying. You can use the ID and password that I am going to share. Someone is asking me like, not able to copy the link. So
No, but I
leave the
think
link.
the link will be provided to them on their STG ID.
Yeah. It will be available in stg.learnity.com also. You can see that
Yeah,
in
so
the bottom. Yeah. Yes,
No,
sir.
no,
You can.
Ranjit, we will
Yes.
not allow them to use any link and password. They have to go there and click. There is no other way. I'll tell you
Fine.
why. Because there are some students here, I mean, not
Okay.
in this class, but in some other classes who are actually not our students, but they are coming into the classes only to create
Okay.
trouble for us.
Okay, sir. Okay. Understood, sir. Yeah.
So all of them have to enter only through their STG accounts,
Yeah.
because that way we'll be clear that you can't share them. I mean, after that
Fine.
also, if you share, nothing we can do, but from our side at least we would have done. Okay.
Okay.
Anyway, yeah, please follow whatever instructions Ranjit is giving. Yeah, fine.
Okay,
Thank
sir.
you.
Thank you.
Okay, here.